these elemental ratios to predict nutrient retention within the environment, biomass production, and resource competition. And it's been coined as a unifying theory in ecology because you can use these ratios to understand how the checks and balances are essentially occurring within the system. And so to kind of like tell you how it works, so say you have a resource, let's say it's algae. You have a consumer, let's say it's a mayfly. And if the mayfly had an N to P ratio that was only what its resource was, the line would be like this. It would be a 1-to-1 relationship. However, that doesn't happen. Think of how you eat. So say you just ate salad every day for the next week. You wouldn't have the same N to P ratio as a salad, as a piece of lettuce. You have a lot more nitrogen and phosphorus than a piece of lettuce. So you have to maintain a specific ratio. What organisms do is we maintain strict homeostasis. So we have a specific nitrogen to phosphorus ratio and a specific carbon and nitrogen ratio. So say you're eating that salad every day, every day, every day. Well, it has a lot of carbon in it. And to maintain homeostasis, you're going to excrete a lot of carbon because you have excess carbon. So you're going to get rid of it. You're going to maintain all the nitrogen, phosphorus, and the rest of the nutrients. So you maintain strict homeostasis. And there's been a lot of talk about how this can influence ecosystems in a very general pattern. So due to this consumer regulation, due to maintaining homeostasis, organisms can have a really large impact on nutrient cycling within the ecosystem. And this paper used a very nice mathematical model to show this. And they showed that if the consumer is in high abundance, they can have a dominating effect on nutrient cycling. And I thought, mussels are really dominant and they're really high in density, so maybe that's what's going on in my system. And other researchers have found, like Bob Hall and others, they showed that this invasive snail species completely controls nitrogen cycling within a Wyoming stream just due to high abundance. Additionally, Pete McIntyre and others showed that fish, due to their aggregating patterns, can cause these biogeochemical hotspots, so hotspots of nitrogen and phosphorus cycling. And additionally, Capps and Flecker showed that these fish in Mexico, which were also invasive, very different homeostatic needs than the native fish. These fish need a lot of phosphorus.